In the example set number 2, if you see the number 1, you are going to see the regular board feeding network. This is the neural network, which has input values and bias. Then all the weights are given in this case, and target value is 1. Then if you see this diagram, you are going to see by using the given weights, it is calculating the x values. We call that those as x values, which are input values for the next layer. So you can think about layer by layer, you're gonna working to get the final layer or output layer. Then you are going to get final output. Compare with the target value. We are going to calculate the error by using our error formula. Then look at if it is making our goal or not. 0.727 is too big, so we are going to make better layer, better network. So one of the easiest way to think about is when you make the backpropagation, you can think about you copy this network structures. So backpropagation network has the exact same copy. It has the same input values, but only the weight and x values are different because backpropagation's goal is finding negative gradients. So we're going to store some values to figure out the negative gradient into each E node. Now the circle becomes an E node. Then on the wire, we are going to write down the final negative gradients of that weight, the corresponding weight. So you start from the final node, the output layer. Final one, you are going to say T0 minus Y0, layer 2. So you are going to use a target value minus real output value. This is final E value. So you are going to store this result at the last E node. You can think about if this is a layer 3, this value is stored at E layer 3. Then you are going to calculate the negative gradient on the last weight. Negative gradients can be calculated as E layer plus 1 times X layer. So you are going to multiply E3 value times X layer is the previous layer's X value, so 0.343. Then when you calculate the next E layer 2 is this circle. E layer 2 will have the sum of weight and E layer plus 1. But there's only one weight and one E layer plus 1. So you are going to do only weight 0.6 times E layer plus 1 is actually 1 plus 0.206, so 1.206 times derivative of the current layer is, in our case, because we are using the transfer function 3, the normal sigmoid function, it is y times 1 minus y, the derivative is. So we are going to use, actually this y represents x layer. X layer represents this y value, the output of this x node. So you can say 0.343 times 1 minus 0.343. So you are going to store that result into the E2. So after you multiply 0.6, actually it's a negative 0.6 times 1.206, the E3 value times derivative of the current node. So I can also say x2 times 1 minus x2, or 0.343 times 1 minus 0.343. Then you have to figure out the negative gradient first of the wire between E2 and E1. So this first wire has E layer plus 1 and times X layer. So E layer plus 1 is E2, so this final result. So I can say E2 times X layer means X1, so 0.297 will be the negative gradient on this wire. Then the second one's negative gradient will be E2 times X layer, so 0.470. Then you are going to find the E node. So E10 will be weight, that means original weight, times E layer plus 1. So there's no sum again, because to come to this E10 node, only one direction exists. So you are going to calculate E10 by doing weight negative 1.08 times E layer plus 1 is like a E2 value, then times derivative of this node is x10, actually 0.297 times 1 minus x10. That's going to be E10, layer 1, 0. Then E11 will be the weight of the wire to coming here is negative 0.7 times E2 times x11 times 1 minus x11. So actually, this is 0.470. Then we need to also get the negative gradients between input layer and layer 1. So you're going to use E10 for the first one. Negative gradient is E layer plus 1, so E10 times X layer, that is 1. So first one's negative gradient will be E10 times input 1. Then second one is E10 times input 0. Third one, E10 times 1. Fourth one, E10 times 1. Then by using this one, the other 4 layers, you are going to use E11. Only one thing, at the end, you do not touch the input layer. So 1011 stays there. Now backpropagation is ready. So number 2, there's an answer, the backpropagation structure. I can name it as a backpropagation network. Then by using this one, the real network can be updated. When you update the real network, you are going to update only weights. Then if you do forward feeding, X values will be automatically updated and you are going to see the new output. If you use those values, very first weight, you are going to use E layer plus 1. That means E3 will be used. So this negative 0.559 are from E3. That means 1.206 times X layer. That is from the previous question 0.343, because that is X2. It is 0.343 times alpha. In this question, alpha was 0.1 plus original weight. The original weight was negative 0.6. So if you calculate this one, you are going to get negative 0.559. You can also get this weight. Negative 1.085 is from E2. So E2 from the propagation times X. This one is actually going to X1, 0. So original X1, 0 was 0.297 times alpha, so 0.1, plus original weight was negative 1.08. Then, if you see the next one, this negative 0.708 is coming from E2 is negative 0.163 times X value 0.470 because now you're supposed to use X11. So from the old forward feeding times alpha is 0.1 plus original weight over this wire was negative 0.7. So by using this rule, you are going to update each wire weight. Then you are going to start the board feeding to get the new X values. So weights are first, new weights, then board feeding, so get new X values. Then you can calculate the new error. This is example set 2.